Hello, my name is Tyler Moore, and this is my XFLR5 video. So for part one of the project, we want to define an airfoil. So we're going to go to Direct Foil Design. We're going to open our Clark Y airfoil that we get off the internet. So that's that there. And then to analyze it, we need to go to File and then Xfoil Direct Analysis. And then from there, we need to first define the analysis. We're going to do that at a Reynolds number of 1 million. We want to do that at an alpha sequence starting at -5 degrees, ending at 20 degrees with an increment of 1 degree. So if we analyze that there, then that gives us the graphs we're looking for. The CL versus alpha, the CL over CD versus alpha, and the CL versus CD. And we can right click and go to current graph and export graph, and we can export all that data to Excel. Now, next for part one of the project, we need to define wings. So to do that, we go to File and then Wing and Plane Design. We'll go to Plane. We'll define a new plane. I'm going to uncheck these two boxes because we just want the wing. Then we'll click on Define. So I found it easiest to use a chord length of 1. These are Clark Y airfoils for the foil section. And then to achieve a different aspect ratio, we change this number here. So for example, an aspect ratio of 4, we change this to the number 2. That's our wing. So go ahead and save that. But before we can do an analysis on that, we need to do a batch analysis here in this screen. So we'll go to File, Xfoil Direct Analysis, click on the Analysis tab and click Batch Analysis. What I did is started at 900,000, went to 1,100,000, which is with an increment of 100,000, and did the same parameters as before, an alpha sequence from -5 to 20. And I just did my max iterations at 100. We'll analyze that. And that'll give us, that'll allow us to run our wing and plane design, our wing analysis. So we'll go to analysis here, and we'll do the same thing as before. We'll define an analysis, and we want a Reynolds number of 1 million again. So we can get that by changing the free stream speed to 15 meters per second. We don't need to change anything else. Keep all that default. Same thing here, we'll do a sequence from -5 to 20 with an increment of 1. These graphs here, and we'll analyze that. And here we can see all those same graphs, CL versus alpha, CL over CD versus alpha, CL over CD. We can export all of those. Now to change the aspect ratio and analyze for the next wing, you go to the plane tab, current plane, and edit wing. Then we'll just change this number to 4, for example, to get our aspect ratio of 8 that's required. So that'll get rid of our data, and we'll just click Analyze again. And then same thing here to get the aspect ratio of 12. Edit wing, change this to 6, save, OK, and analyze. Once we export all that, the first part of the project's done. So starting on to the second part of the project here, we need the lift curve slope. So here I have all my CL versus alpha data in different sheets here. And to get the lift curve slope, we use the Excel's trend line function. And so I use the trend and the slope functions here instead of doing trend lines on the graph because I found that easier. And I tabulated all of those. So this is for the airfoil and each aspect ratio wing. And these are the lift curve slopes I got. Then I get the maximum CL, it's pretty straightforward. This is our CL column here. We have that on each spreadsheet. And then we can just get the maximum from those here and the alpha at which they occur. And the maximum CL over CD we can get from the CL, CD versus alpha spreadsheet. See that here? So this is our CL versus CD values here. We can take the maximum there for each one. And tabulate that at the alpha in which they occur. And the next is the zero lift drag coefficient. That'll be here. And so what I did is I just figured out where it crossed the x-axis and found the data values where it does that, where it changes signs. Then I use Excel's forecast function to find where it actually crossed the axis. So that's what I found easiest and tabulated that here. Now we go back to XFLR5 to do the 7 degrees angle of attack part of the project. So here we want the local induced drag. So I'm going to go back to an aspect ratio of 4. That. And we don't want to sequence anymore. We just want to change this to an alpha of 7. So we'll go ahead and analyze that. If we go to this tab here, we can see our induced angle of attack. And we can export that, obviously. And then if we right click, we can click on current graph, define graph settings, and we can change this to the local induced drag. Induced drag coefficient, there it is. And we can export that as well. And we can do that for each aspect ratio wing, which I'll show. Save, okay. Analyze. Get the idea, and then we can change this back to induced angle if we wish. So that's that part. And then the last part of the project, it requires us to go to our CL values and calculate things. So for each aspect ratio wing, this is alpha 7 degrees and then our CL value. So to get the induced drag coefficient, I just use the equation CL squared over pi times the aspect ratio, and we're assuming that E is equal to 1 here. And so that gives us that value here, same thing, multiplied by the aspect ratio. That gives us our induced drag coefficient. And the induced alpha value, we use the equation coefficient of lift over pi times E times the aspect ratio, assuming E is equal to 1 again here. That gets our alpha induced in radians, which I also converted to degrees. Then our downwash velocity, we use the equation, the arctangent of the induced alpha value times our velocity, our free stream velocity, which, as I showed before, is 15 meters per second in our simulation. So that gives us my downwash values. That covers all the project. Thank you for watching.